Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. We've seen how the mean value theorem works for simple parabolas, but on the AP or IB exam, you'll see it used to prove existence or find speeds in complex contexts. Today, we're going to tackle a couple of exam-style problems, as well as prove the mean value theorem itself. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first question, we have f is a differentiable function such that f of 2 is equal to 5, and f prime of x is less than or equal to 3 for all x. The question is, what is the maximum possible value for f of 5? Now, by telling us that f is differentiable, we can automatically conclude that it is continuous, which means we can now use the mean value theorem. So we're going to let our a be equal to 2 and our b be equal to 5. So by the mean value theorem, there exists a c that is in between 2 and 5, such that f prime of c is equal to f of 5 minus f of 2 over 5 minus 2. Now, since f prime of x is less than or equal to 3 for all x, we have f prime of c is going to be less than or equal to 3, which is equal to f of 5 minus f of 2 over 5 minus 2, which is 3. Now, multiplying both sides of this inequality by 3 is going to give us 9 is greater than or equal to f of 5 minus f of 2, which is equal to 5. So therefore, f of 5 is going to be less than or equal to 14. So therefore, the maximum possible value for f of 5 is going to be equal to 14. For our next problem, we're going to prove something that seems a little trivial, because intuitively this makes sense. We want to prove that if f prime of x is equal to 0 for all x in an interval ab, then f is constant on that interval. And this makes sense because if the derivative is 0 within that entire interval, then that means our graph is going to be flat. So how do we actually prove this? We're going to start by letting x1 and x2 be any two distinct values in the interval AB, such that A is less than x1, which is less than x2, which is less than B. Now, we're given that f prime of x is equal to 0 for all x in the interval. So this means that f is differentiable. So we have f is differentiable, and because it's differentiable, it is also continuous on the interval x1 to x2 and the closed interval x1, x2, respectively. So now we have the conditions required in order to use the mean value theorem. So by the mean value theorem, there exists a number c that is in the interval x1, x2, such that f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. Now, since f prime of x is equal to 0 for all x in the interval AB, and our value c, which is in x1, x2, which is a subset of our interval AB, c is in the interval AB. So therefore, we have f prime of c is going to be equal to 0, which is equal to f of x2 minus f of x1 divided by x2 minus x1. Now we can multiply both sides by x2 minus x1. And once we do that, we get 0 is equal to f of x2 minus f of x1. And then moving one term over to the other side, we end up with f of x1 is equal to f of x2. And now, since we have chosen our x1 and x2 to be arbitrary points within the interval, this means that the function must take the same value for every x within that interval. So since x1 and x2 were arbitrary points in AB, we have f of x must be equal to c for all x value within that interval. And thus we have completed our proof. And then for our last example in this video, we're going to go ahead and prove the mean value theorem. We're going to start by writing down the secant line equation. So the secant line is the line that connects the point at A to the point at B. So that equation is y is equal to f of A plus f of B minus f of A over B minus A times x minus A. If you have trouble seeing this, this is really just the equation of the line in our point slope form, because this here is the slope of the line, and then the point is, so our point here is A comma f of A. So we have really y minus f of A is equal to the slope multiplied by x minus A. Next, we're going to define a function capital F of x, and this is going to be the difference between our function f and this secant line. So this is going to be equal to f of x minus our secant line equation. So that's going to be minus f of A minus f of B minus f of A over B minus A times x minus A. So now note that at our endpoints, f of A is equal to 0, and f of B is also equal to 0. And since our function f is continuous on the interval AB and is differentiable on the interval AB, we can conclude that our function capital F is also continuous on the closed interval AB and differentiable on the open interval AB. And the reason is because our function f of x is defined as the original function f of x minus the equation of the secant line, which is just a linear equation. And now we can go ahead and use Rolle's theorem because we have the function being continuous and differentiable, and we have that our starting point and our end point have the same value. So therefore, by Rolle's theorem, there exists a C within the interval AB such that f prime of C is equal to 0. So let's go ahead and first find the derivative of our function capital F. So we have capital F prime of x is equal to lowercase f prime of x minus derivative of f of a is just 0 since that's a constant. And then we have minus f of b minus f of a over b minus a, which means capital F prime of c is equal to 0, which is equal to lowercase f prime of c minus f of b minus f of a over b minus a. And then finally, isolating f prime of c is going to give us f prime of c is equal to f of b minus f of a over b minus a, which is the conclusion of the mean value theorem. And now let's go ahead and do a quick recap of what we covered in this video. The mean value theorem is often used to find the maximum or the minimum possible values of a function when only the derivative's range is known. And we saw that the proof of the mean value theorem relies entirely on shifting the function so that it satisfies Rolle's theorem. And again, it's important to remember that the mean value theorem is an existence theorem. All it does is that it tells you that a point exists, but it doesn't tell you where it is. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.